Alright, now let's look at the difference of continuous random variables. So suppose we know the following. The mean weight of a male llama is 335 pounds with a standard deviation of 27 pounds, and the mean weight of a female llama is 287 pounds with a standard deviation of 24 pounds, and the distribution of the difference between the male and female weights are normally distributed. What is the probability that a female llama weighs more than a male llama? Alright, so initially, not a lot of sense going on here. Why do we care about the llamas? And if we know that the males are 335 and the females are 287, then we can suspect that most times the males are going to weigh more than the females. So why bother to do this calculation? Well, both of these distributions here, they'd have their own normal curves, and when we would look at the overlap, we might see some observations that disprove this. But also, we are specifically looking at the difference between male and female. So that's assuming this relationship here, male minus female. Okay, so let's go ahead and define our parameters here. So if I'm looking for the difference, and I'll let male be x and female be y. If I'm looking at the difference between male and female, then we're going to take the difference of the means here. So for that, that'll be 335 minus 287, which will give us 48, and this will be pounds. And then if we look here at the standard deviation of the difference, remember we never subtract their standard deviations, but since we're looking for the distance here, we're going to combine the variances. So we can add the variances. We cannot just add standard deviations, because the standard deviation measures the distance between observations and the mean. That's why we have this radical here to account for that positive value. So let's take our standard deviations here. Let's find our variances. And remember, to find the variance, you square the standard deviation. So we'd add those squares, take the square root, and we'd get an approximate standard deviation of 36.12 pounds. And I'm just going to verify that. I don't know why that number is not sitting right with me. So let's go ahead and check it out. And okay, no, we're good. 36.12 pounds is reasonable. So let's start with our parameters for this distribution. We know that we're looking at the weights here, and so our distribution, right, the distribution of x minus y is going to be distributed normally with a mu of 48 and a sigma of 36.12. Now, based on that, I can draw a picture of the situation. So I'm going to go ahead and draw in our normal curve here of the differences. So I standardize this each time. Again, you don't have to, but for me it helps to see where the observations fall. And I know here at the mean we'd be at 48, one above, you'd be 36.12 above, so that would be about, this would be 84.12 here at 1, and then below would be at about, let's see, that'd be at about 11.88. And then, of course, this pattern would follow throughout the rest of the distribution. Well, notice that our difference initially was given to us between male and female. And here I'm asking, what is the probability that the female weighs more than the male llama? So whenever I'm looking for the difference, we can actually make an assumption about this difference. So specifically, if we assume there is no difference, then we assume this case here. And I'm going to write off to the side. So here are some condition checks. So if we assume there is no difference, and we're saying if there's no difference, then that means male minus female would be 0, since the males would equal the females at all times. Okay, which means now if we use some inequality notation, if we do males minus females and this value is positive, then reworking this equation, we get this is where male llamas weigh more than female llamas. Well, what if we look at the difference now, and the difference is negative? Well, based on that, then we get that males weigh less than females. This is the condition that we are wanting here. So I'm actually going to look for where this difference is less than 0. And that's why it's important to have a picture here. Because now what I can do is I look for 0 on this curve, and this is where it gets kind of tricky. I'm not looking for a standardized 0, because if it were a standardized 0, it would put me right at the mean. I'm not looking for where the male and the females weigh exactly 48 pounds. I'm looking for where the females weigh more than the males, which is 0 in terms of the observation. So that's not going to go on the standardized normal curve. That's going to go on our observation curve here. So that's going to put us somewhere between -1 and -2, because the 0 would go right here. This is 0 pounds. And that's because if I take another standard deviation away from 11.88, I end up in the negatives. Now, again, because of this 0 and our conditions, we know that at this value, they're equal. When we are greater than this value, when it's positive, the difference is positive, that means males are greater than females. What I'm looking for is that the difference is negative. So I'm actually going to shade to the left here for this situation. So I've got my parameters, I've got a picture, and now I can actually find the probability of this event happening. So I want the probability that an observation, right, the difference here is less than 0, right? Because I'm looking for where the males minus the females are going to be negative, such that the females weigh more than the males. Okay, so then what we can do from here is we can convert this to a z-score such as the following. Now to find the z-score, again, we need our two parameters, which here's the mu, here's the sigma, and then here is the observation. So we can find our z-score as follows. So the z-score would be the observation minus the mean over the standard deviation here. And this is going to give us approximately -1.33. So I'll write that in here. So the probability of finding a difference that is negative would be the same thing as finding an observation with a z-score that is less than -1.33. And we check our conditions here. Well, -1.33 is most certainly between -1 and -2. So we're on the right track. And then here we would just go to our probability tables, table A, and we would find that the probability of this difference is, I actually don't have my normal table, whoopsies, so let us check here, the lower bound. See, and I always do the calculations by hand so that you all know, like, I wouldn't ask you to do anything I don't do myself. Okay, I did something terribly, terribly wrong. Empirical rule. Why, calculator, do you not want to work? Let's do, oh, because I did the wrong one. Okay, let's see. 48, 36.12. Okay, let me try this again. Okay, and I got 0.0919. And this just would have been easier for my table, which is why I prefer the tables, but I don't have my table at home. So I had to go to the calculator here. But either way, you would be able to obtain this result here. So there's actually a 9.19% chance that the female llamas will weigh more than the male llamas. So just as a quick recap here, we looked at the difference, which was listed for us as the difference between male and female. We found our parameters for this combined random variable, this continuous random variable. So I found those here. I listed my difference as normally distributed by the parameters. Drew a picture of the situation, and finding which area to shade came from these condition checks. So I could have found the probability they were equal, the probability that a male weighs more than a female llama, or what we found, which was the probability a female llama weighs more than a male llama. And then the rest of the logic follows the same way. Give a probability statement, give a z-score, and then find the respective probability for the situation.